This is part of the Testicular Puzzles story. This one, why is there such variability in testis size? And just for interest, this is a right whale. It's the largest testis of any animal in the world. Each testis, remember it's got two of them, each testis weighs 500 kilos. 500 kilos. One sperm is only needed to fertilize an egg. Let's just remind ourselves what the testis is doing. The testis has two main roles, sperm production and testosterone production. The sperm come out and go through the tiny efferent ducts into the epididymis, through the epididymis, and then eventually out to the vas deferens. But the testis, main function, sperm production, testosterone production. Then here's a cross-section of the testis again. Here are the seminiferous tubules, lumen in the middle where the sperm are being released, small amount of space between the tubules occupied by the blood vessels, the lymph and the Leydig cells. So the predominant determinant of testis size is the volume of the seminiferous tubules. And here's a cross-section of the wall of the seminiferous tubules showing adjacent Sertoli cells in the blue, the developing sperm going upwards between the adjacent Sertoli cells and liberated in the middle with a spermatogonia at the outside. And the basic idea is because of the relationship, the very close relationship between Sertoli cells and the developing spermatogonia or spermatocytes and spermatids and sperm, each Sertoli cell has a very fixed capacity about how many sperm it can actually support, how many germ cells it can support. Therefore, the number of Sertoli cells in the testis really determines the sperm production of that testis. And the number of Sertoli cells in the human testis is remarkably variable. Here we see a plot of the number of Sertoli cells which are actually found in human testes. These are from men who died suddenly. The testes were looked at, and we have enormous variations, very low numbers, almost a tenfold variation in Sertoli cell number between different men. And that variation in Sertoli cell number is reflected by the sperm counts. Here we are, fertile men, enormous variation. This is just a cross-section of the general population, and in infertile men in this particular study it was a bit lower. So huge variations in sperm count. This begs the question, how many sperm are actually needed for fertility? And the data we have is, this is from Lancet in 1998, looking at reductions along here of sperm concentration in normal semen, and we can see that when you get down to below about 20 million per mil, it begins dropping, and it goes down and down and down until if you get below about 1 million per mil, then the chances of fertilizing an egg are very low, 1 million per mil. So what's the difficulty with developing a hormonal male contraceptive analogous to the female pill? Well, the kind of headlines like this, birth control male contraceptive injection shows promise, comes up year after year. And there's always, it's just on the horizon it seems, but it never quite reaches there. What's the problem with male hormonal contraception? To understand male hormonal contraception, let's just look again at female hormonal contraception. The original idea about the contraceptive pill was to interfere with this system, where the hypothalamic control of the anterior pituitary produced FSH and LH, that stimulated the ovary produced the eggs once a month, and the steroids which feed back onto this system. The idea was to interfere with that system. How to interfere? Well, essentially to increase this negative feedback. So steroids for most of the cycle feed back negatively onto the hypothalamic pituitary system to suppress FSH and LH. So the idea was this: if we can increase the negative feedback by administering the steroids which normally feed back negatively, things like progestogens and estrogens, that would suppress FSH and suppress gonadal function. And that worked, giving progesterone and estrogen, and especially because you could give them orally, which was very convenient, you could do exactly that. Increase the negative feedback, suppress this system, and if you suppress that system, you suppress gonadal function, you suppress ovulation. A sure way of preventing conception. And this looks at the time course of the events. Essentially, the clinical trial started in 1956. In 1959, the first oral contraceptive was approved for human use, but gradually it became clear there were side effects associated with contraceptive use. And those adverse side effects then caused a search for how could you still have a contraceptive pill but without the side effects. And those side effects could be reduced by reductions in the amount of estrogen you were giving, and then changing in the particular types of progestogens you were giving as well. It became apparent that the contraceptive steroids could have a variety of sites of action, and that variety of sites of action contributed to their very effective nature. So, as well as feeding back onto the LH and FSH and maybe inhibiting ovulation, they didn't all have to inhibit ovulation because there were other sites of action. Other sites of action, such as on the uterus, affecting the precise sequence of hormones which allowed for receptivity of the uterus to an implanting blastocyst. To sperm entry, progestogens in particular make the mucus much thicker here and make sperm entry much more difficult. And then postcoital pills, where you affect various things after coitus, after intercourse. What kind of things? Well, it's most likely to be interference of implantation and uterine and fallopian tube events, which allow proper fertilization and embryonic development. So a whole variety of sites of attack for the contraceptive pills in females. So if we now look at the principle behind the initial thoughts about the principle of a male hormonal contraceptive, they followed along exactly the same lines. That is, if you could increase the negative feedback here onto the hypothalamic pituitary axis and then suppress FSH and LH, you should be able to stop sperm production. And that's what happened. So they said, okay, let's increase this negative feedback. And how are we going to do that? Let's give, progestins will increase the negative feedback. Testosterone will as well. If you increase the negative feedback, or you could add something else, a GnRH antagonist, which shuts off this system. So both of these things, either alone or in combination, would suppress FSH and LH, and therefore spermatozoa production and testosterone production would go down. And this was initially sort of a good idea and in many ways highly effective. But, and this is an important but, a small percentage of men fail to show sufficient suppression of sperm even when FSH and LH levels were suppressed very low. So you could suppress these, but in some men sperm was still being produced. And that was a problem, because even a low number of sperm can still produce fertility. So if you suppressed FSH and LH, why is it sperm can still be produced in some men from the testis? You'd expect nothing to be happening. What's going on? A clue to what might be going on comes from looking at prepubertal boys. So this is essentially the system in prepubertal boys. There is very little GnRH coming out of the hypothalamic system to drive the pituitary, therefore there's very little FSH or LH. They've got small testes, they're not producing sperm, neither are they producing testosterone. And there's very little negative feedback. But occasionally spermatogenesis can be found to occur in the testes of prepubertal boys if they have Leydig cell tumours. Now, Leydig cells are the things which produce testosterone. So prepubertal boys with Leydig cell tumours are producing a lot of testosterone. And that's where spermatogenesis can occur. And that raises a question that it may be that if there's a lot of testosterone being produced locally within the testis, maybe local steroids are important in spermatogenesis. And maybe local steroids can really drive spermatogenesis themselves. And perhaps this is what's happening in the men who fail to show sufficient suppression of sperm under conditions where FSH and LH have been shut off. There's still sufficient testosterone or 5-alpha dihydrotestosterone within the testis to drive some spermatogenesis. So that's a problem which has still got to be overcome. So how close are we to a good hormonal contraceptive in men? Well, the trouble is the attributes of a good contraceptive are like this. You want it to be effective. In essence, a hormonal contraceptive in men is almost there. It is effective, but you've got this problem with variable responses. In a few men, they seem to escape the suppression of LH and FSH. Rapidly acting. Well, again, yes, sort of, but no. Spermatogenesis is a long process, takes a couple of months, and then you've got a couple of weeks going through the male reproductive tract, the epididymis. So if you're affecting spermatogenesis, it's a long time before you actually see a contraceptive effect. Cheap and reversible, yep, both those attributes are okay. Easily administered. Well, how are you going to administer the steroids? In women, you can give orally active steroids. It's much more difficult to have orally active testosterone. And so generally, the focus has been on intramuscular injections or subcutaneous implants, or even transdermal gels or patches, none of which are as convenient as an orally active compound. Minimal adverse side effects. Yes and no. The trouble is with testosterone, if you're giving a testosterone, because you have to give testosterone to actually make sure that the men are not physiologically castrated and lost all their testosterone, you have to give testosterone back. And that testosterone going back can cause a whole series of adverse effects. And acceptable to both sexes is a male contraceptive. If a man says, oh, I'm taking the male contraceptive pill, would a female trust him? So let's go back to that headline we saw at the beginning. Birth control male contraceptive injection shows promise. It went on to say this. US researchers say the jab was almost 96% effective. Well, 96% effective is fine, but 4% it wasn't fine in, and you're not 4% pregnant, you're 100% pregnant. You can't afford a 4% failure rate. And the researchers stopped taking on new participants after concerns were raised about side effects such as depression and other mood disorders, as well as muscle pain and acne. So this particular study was no good, but the search goes on. The hope is always still there. There may be an effective, acceptable, no side effects male hormonal contraceptive, but we're not there yet. Okay, let's go back to the original question. Why is there such variability in testis size? You only need one sperm to fertilize an egg. In men, you produce 150 million sperm per ejaculate, perhaps, or more than that. You don't need all of those. Why are there so many sperm being produced? People often think about natural selection and survival of individuals, but really natural selection works not on individuals itself, but the ability of those individuals to pass their genes on to the next generation. So selection pressures are really on the success of any reproductive pairing. And if you look, there is enormous variability in reproductive mechanisms, driven by the enormous selection pressure on the success of each reproductive pairing. It's easy to assume that because humans tend to be mainly monogamous, that is, a single female pairing up with a single male, often for a very long period of time or throughout their whole lives, it's easy to assume that that condition exists throughout the animal kingdom. But there are many variations on that theme, with one male pairing with many females, or many females pairing with many males, and many males pairing with many females in the same species, really very promiscuous. And maybe a single female just mating with more than one male. How common is it, females mating with multiple males? Well, a study was done where they looked at a whole number of different species. Species from amphibia to spiders, to birds, to insects, to mammals, to reptiles. And polyandry was found in every one of the major groups they looked at. How many of the females mated with more than one male in any population? It depended on the species. In some species it was 100%. In others it was 50%. In others it was just 5, 10 or 15% or so. But it was very common. So throughout nature it seems that it's very common that females may mate with more than one male. And in doing so they'll produce offspring, litters, clutches of eggs, or successive single offspring, which have multiple mixed paternity. What's the selective advantage of this? Well, the answer is probably that the selective advantage comes from the offspring will have greater genetic diversity than if they just, the female always mated with one male. All the offspring will have the mother's genes, but with a variety of genes from a selection of different males. So essentially we now have the situation where there is competition between males to mate with a female. All the offspring will have half of her genes, but will they have his genes or his genes? There's competition. Does the female choose the male? Do the males fight each other? What happens? Such competition for mates gives rise to sexual selection and enhances secondary sexual characteristics. Sexual dimorphism in bird plumage is very obvious. Happens in butterflies. Sexual dimorphism in shape, body shape, total body shape, small male spider, large female spider. Males will display to each other or to the female. Males will fight each other. Here we have two stags. The dominant one will mate with the majority of the hinds. So classically, sexual selection is really seen like this. Male-male competition fighting, or rather gaudy males, and the female making some choice between the ones that she fancies most. These are pre-copulatory mechanisms of sexual selection, the males fighting each other before mating with a female, or the female making a choice between males before she mates with one of them. But we now understand that some selection takes place post-copulation. So the sperm are delivered to the female tract, but then there's competition between the sperm, either in terms of competition between the sperm themselves, which one gets to the egg first, or the female may make a choice about which sperm to use. So how is this relevant to variations in testis size? The variations are enormous. Here's a ram, 200 grams each testis. Compare that to humans, just 20-25 grams or so per testis. Huge variations. Why? Well, the first answer is fairly obvious. Rams live in a flock situation and mate with a number of ewes per day, maybe 3, 4, 5, 6 or more. There may be 35, 50, up to 100 ewes in a flock. So lots of matings. Humans are much more monogamous and have sex less often. The variation in Sertoli cell number is reflected in the variation in testis volume in men. Here we have testis volume, combined testis volume this time, going from very low volumes to very high volumes here, looking at how that relates to sperm number, how many sperm they ejaculate. Enormous variation, but essentially a relationship: the bigger the volume of the testis, the more sperm you're likely to produce. Variations in testis size occur within closely related species. Here's the gorilla: body weight 170 kilos, testis size 30 grams. Chimpanzee, body weight 44 kilos, testis size much bigger, and compared to body size 16 times bigger. Relatively bigger testes in this chap. Why? Well, it comes down to really, there's a single male dominant gorilla, the silverback, which mates with essentially his harem of females. So it's just him, no competition with other males. Chimpanzees, there is lots of competition. Many males will mate with the same female. There is competition, intense competition between adult males. So the take-home message comparing these closely related species is that the more testicular tissue you have, the greater potential for sperm production, and that will maximise chances of reproductive success. So during the course of evolution, bigger testis size has slowly evolved in chimpanzees compared to gorillas. This relationship between testis size and the competition between males for accessible females for mating seems to be a general principle. It certainly applies to other primate species and other species as well. In primate species, we have two things here. One is testis mass, log scale, body mass, also a log scale. All the blue dots refer to primate species which the females mate generally with just one male. All the red dots are where females are likely to copulate with more than one partner every time she comes into heat. And you can see there's a clear relationship between more than one male is up here, bigger testes, just one male down here, smaller testes. The association between reproductive characteristics and competition between males goes much wider than just simply testis size. Alan Dixon reviewed this very nicely in Primates. He's an expert on the whole subject in 2018. And the next few slides we'll look at some of the data that he presented. Here we're looking at seminal vesicle sizes. Primates with just a single partner essentially had smaller seminal vesicles than those with multiple partners. In terms of seminal coagulation, the seminal coagulation was much less in primates with just single partners compared to those with multiple partners. In mammals which just mate with a single partner, the vas deferens tends to be longer. Multiple partners, vas deferens shorter. Single partner, the vas deferens is thinner. Multiple partners, thicker. Dixon argues that this is really to maximise copulatory success, expelling sperm as quickly as possible into the female tract. The shape of the penis in primates is also remarkable. And looking at the various sizes and shapes of penis, he came up with this kind of analysis. He scored various things like the length of the penis, whether or not a baculum was present, and if it was, the length of it, the complexity of the end of the penis, the shape of it, whether or not the small penile spines were there. And the results were clear. All of these grey bars is where there were multi-partner mating systems, so essentially competition between males. The open bars is where there were single partner mating systems, much less competition, if any at all. So the take-home message is clear. Variability in the characteristics of the male reproductive system, whether we look at testis size, seminal vesicles, vas deferens, the penis, that such variability often correlates with whether or not there's competition between males for access and mating with a female. The whole topic of competition between males and sperm competition really arose in insects initially before it was extended to mammals. And if we just go back to insects right at the end here, we can see the remarkable adaptations that can occur. This is the penis of a damselfly. Why is it such a funny shape? Well, because it really inserts itself into the female and tries to get rid of previously deposited sperm. So sort of catching the spermatophores that have already been deposited and drawing them out and getting rid of them for his own sperm to be deposited. Other species, the sperm are displaced or moved within the female tract to a place within the tract which makes them less likely to fertilise eggs. And some species produce plugs, mating plugs, coagulated plugs, to prevent other males from actually getting in, from mating with the female. The same thing happens in rodents. If you want to read more about this, Penis Evolution Across Species, Divergence and Diversity, Nature Reviews of Urology, Volume 16, pages 98 to 106, 2019. Well worth a read. The review of penis evolution across species, divergence and diversity contain this figure. Up to now we've really been dealing with this one. Pre-copulatory mechanisms of sexual selection. Some of the factors influencing male reproductive traits. But what about this? Post-copulatory mechanisms of sexual selection. The sperm competition. Female choice once the sperm have got within the female tract. What's happening here? We're going to be dealing with sperm wars. A big subject, a huge subject. And this is a good review which sets the background very nicely. It was published in Reproduction, the journal Reproduction, in 2012 by Simmons and Fitzpatrick. This is really the concept. Is there a great sperm race? The idea is that if a male ejaculates, millions of sperm, they're all racing towards the egg. The one that gets there first, the one that wins the race, wins the ultimate prize of fertilizing the oocyte. Is this really true? Is the competition between sperm of the same male? If more than one male's mating, whose sperm are they? Is this the mixed ejaculate, where this one may belong to male A, this one may be male B, male C, male D? Whose sperm are they? Which one wins the race? Is the concept of a great sperm race really valid? Here's a very simple experiment showing that sperm are not all equal. The semen from two boars was pooled so that the pooled semen had equal numbers of sperm from both boar A and boar B. This pooled semen was inseminated into 32 females, and the expectation was that if all the sperm were the same, then half of the offspring would be sired by boar A, half the offspring should have been sired by boar B. No, not at all. Boar B was very much more successful. 70% of the offspring came from him, only 30% from boar A, even though they both contributed equally in terms of sperm numbers. So there's sperm competition within the female tract. So the take-home message, equal numbers of sperm does not mean equality of fertility, suggesting sperm competition. Let's go back to what we were looking at earlier. In some species, the female may mate with many males. There's competition between the males. And here we are in rodents, competition between males. The polyandrous species tend to have longer sperm. Why? Well, the answer seems to be that longer sperm probably swim quicker. Looking at a whole variety of different mammals, the longer the sperm tail, the quicker they can swim. So generally selection pressures, if there's a race for the egg, selection pressures might be expected to favour those sperm which could swim most quickly. We'll be looking at this in a later section. That kind of argument would fit this kind of data. Sperm swimming speeds in primates. If we look at the gorilla, where we have a single dominant male, little sperm competition in terms of mate competition with other males, he has slow swimming speeds for his sperm. The chimp, where there is competition between males, much faster swimming speeds. We're going to leave this subject now, but is it a bit too simplistic? Is it just simply swimming speeds? Probably not. Is a competition between sperm? Definitely. Is a competition between sperm of different males? Definitely. But is it just sperm swimming speeds? What really happens in the female tract? We'll try and pick up some of these questions later on.